All right, so today we're very happy to have joining us Joop Schaye from Leiden. Joop got his PhD at Cambridge University and then was a member at the IAS. And then they got him to come back to Leiden, where he's been ever since. Joop has contributed to many topics in galaxy formation and cosmology. Particular numerical simulations, including hydrodynamics and feedback, as well as detailed studies into absorption spectra of quasars, among many other things. And today he's going to tell us about the Eagle simulations.
Thank you. Yeah, very happy to be here. It's been a very long time since I was here. It's a very, I enjoyed the Blackboard talk earlier, Vibrant Institute. Won't be a Blackboard talk today, but feel free to interrupt me if you want more discussion. So I'll talk about cosmological simulations of the formation of galaxies. And I've divided this up in 3 parts. I'll start with a very brief introduction on what cosmological hydrodynamics means, for those of you who are not familiar with that. And then I will paint a picture of galaxy formation that kind of is what we got out of our previous simulation project called OWLS, and that leads into the new one that we just, well, we just published it, but we've been working on it for many years, and it's called Eagle, and I will give some results from that. So first, what do I mean by cosmological hydrodynamical simulations? So what I mean is that we simulate a representative part of the universe, so not just one object, one galaxy or one cluster, representative part. And we start also at an early time, so from cosmological initial conditions, linear perturbation theory. And we go down to whatever redshift we're interested in, which for reionization could be a redshift 10, but at the simulations I'll talk about today go all the way to redshift 0. In these kind of simulations, we do not have some kind of dark energy fluid explicitly. The expansion history of the universe, the solution of the Friedmann equation, is just imposed as a coordinate transformation. So we use co-moving volumes. The initial conditions these days are quite well known, although it's still of interest to do these kind of simulations also to compare with cosmological parameter measurements. And we're doing this for larger scale simulations than I'll talk about today. But for the purpose of this talk, for galaxy formation, it's essentially known from the cosmic microwave background and large scale structure what the initial conditions are. If you're simulating a representative part of the universe, then the natural boundary conditions are periodic, such that you don't get any edge effects. And in that case, you need a cube. So we're simulating cubes. What's in those cubes is cold dark matter, sampled by particles, gas, which will also sample by particles. And some of those gas particles are converted into stars. We also include radiation, but in the simulations I'll present today, we don't do radiation transport. We assume everything is optically thin. So we basically just compute how much emission is generated as a function of density, temperature, and the UV radiation field that's impacting on the galaxies, so the cooling rates. Simulations you have to discretize. Every simulation is discretizing time when you do an evolution. Then you have a choice whether you do mass or space, and we will be discretizing mass, so we do SPH, smooth particle hydrodynamics. The gravity and the hydrosolvers is 2 of the essential ingredients. You can also do radiation transport or magnetohydrodynamics. We're not doing that. There's been some improvements in how to do the hydrosolvers, and we've taken some of these improvements into account, but it's not so important for the results that I'll present. What is very important is the subgroup models, and I'll talk a little bit about that. So the recipes of what happens below the resolution limit of the simulation. I think it's important to start with some considerations of the resolution requirements, because those are not always taken into account. And it immediately tells you what kind of things you can and cannot do. So if you want to do hydrodynamics, then the basic scales you have to resolve are the gene scales. That's the scale over which pressure and gravity are in equilibrium. So if you write that down, the gene's mass turns out to be at about 10 to the 7 solar masses for a density of 0.1 particles per cubic centimeter and a temperature of 10 to the 4 Kelvin. And at those densities and temperatures, you get a gene's length of about a kpc. Now, why did I choose those numbers? Well, 10 to the 4 K is the natural temperature to choose because it's the warm interstellar medium. It's also roughly the temperature of the intergalactic medium, photoionized gas. That density of 0.1 particles per cubic centimeter is also typical for the warm interstellar medium. It's also roughly the density above which you first can form a cold phase when you have enough shielding, for example, from the UV radiation. It's kind of a limiting case that you could assume. So if you want to simulate that with that resolution, you want to resolve this phase, you need a particle mass that's much smaller than the GeNS mass, so much smaller than 10 to the 7 solar masses, and a spatial resolution that's much less than the GeNS length, the kpc. Now that's quite doable in a cosmological volume today. So we can do that. Now suppose we want to take the next step and we want to include a cold interstellar phase. And suppose we do the minimum, the least difficult cold phase we could do, and let's just say that at this pressure we go to a cold phase. And a cold phase, I'll say, is 100 Kelvin, which is quite warm for a cold phase. So the density becomes 100 times larger. So if you then do the scalings, then what you then get is that your GeNS mass is reduced by 4 orders of magnitude, and your GeNS length is reduced by 2 orders of magnitude. So it immediately becomes too difficult to do in cosmological simulations. You cannot do 4 orders of magnitude more particles. You can just do that in a representative volume of, say, 100 megaparsec, but that's about it. So in a cosmological volume, where you do not just one object, but a representative sample, there is just no way you can do a cold interstellar phase at the moment. And that won't change in the next few years, because we're talking about a factor of 10,000. And it's actually much larger than that, because a real cold phase, you want to resolve 10 Kelvin at least, and therefore also a higher density. So this actually becomes several orders of magnitude smaller. And not only that, you don't just need a resolution. If you wanted to do that, you need radiation transport, because self-shielding is critical in the transition between the cold phase and the warm phase. If you expose cold gas to the ionizing radiation, it gets warm and expands. And if you want to do that, you need to include the molecules, right? And that means complex chemistry. You need at least something like 25 molecules to get the cooling rate roughly correct down to about 100 Kelvin, and much more if you go to lower temperatures. So that's a very difficult problem. It's a problem that can be solved if you simulate just one galaxy, not for a massive galaxy even, but for a dwarf galaxy. And several groups are doing this. Norm has been involved in some of those efforts. We're doing some at Leiden as well. But I won't talk about it today. Today we'll just try to resolve this scale, and that's it. And then we will impose an equation of state on the denser gas that limits this GeNS mass to a constant value. So that we can, and that's what we can resolve. So keep in mind, if somebody's saying they do all the physics from first principles, no subgrid, they need all this, they do all the cold phase, that's just not believable unless it's one dwarf galaxy. Now, people have been trying to simulate galaxy formation for many years, and they have not been very successful. The galaxies turn out to be too massive, they're too compact, they form too early, and they're too round. That's been the story for a long time. Now, recently that has been changing. First, using simulations of individual galaxies, where people did try to calibrate their simulations, of course, to get things right, but still that you could manage is still a success. And later it became more natural to form galaxies that are not too massive, too compact, too old, and too bulgy. Now, why is that? Why did it get better? Well, if you ask different people, you'll get different answers. But to me, it's absolutely clear that the critical thing is that the feedback that people implement from star formation has become more effective. And it's become more effective partly because of higher resolution, but mostly because people become aware of numerical radiative losses that I'll come back to and try to do things to circumvent that. For the high mass end, the other thing that has helped a lot is that there's a new feedback channel that people started including, which is AGN feedback from accreting massive black holes. Now, why do we think we need two different feedback channels at least? One from AGN and something from stars. And that you can see if you compare the dark matter halo mass function to the galaxy mass function. That's the number of objects per mass. This is a plot I've taken from Andrei Kravtsov. What you can see is that even if you shift this to the left by the universal baryon fraction, you get a deficit that increases towards the low mass end and also increases from the knee to the high mass end. If you have just a single feedback process, it's difficult to get it to be first less efficient as you go to higher masses and then more efficient. And so in general, it's more natural to have two feedback mechanisms. Maybe many more, but at least two different classes. Now I'll talk a bit about self-regulated galaxy formation. And I'll start very simple, and then we'll get a little bit more surprising results. So what is self-regulation? Well, it just means what do you get when you have a feedback loop. So if the feedback is too weak compared to accretion, and it could be feedback from star formation or from accreting black holes, then the gas density goes up. If the density goes up, the star formation or the black hole growth rate goes up, and then you get more feedback. Right? So at some point, it's no longer going to be too weak. If the feedback is too strong, you blow out gas, the density decreases. The density decreases, your star formation rate and your accretion rate go down, and at some point, it's no longer too strong. So if you have a feedback loop, you generally tend to go to an equilibrium, or at least a quasi-equilibrium. So that's the basic idea, which is as old as the field of galaxy formation. Now, what are the consequences? Well, the first consequence I already mentioned, galaxies tend to a quasi-equilibrium, where the outflow rate roughly balances the inflow rate. And that doesn't have to be the case instantaneously. That's particularly clear for AGN feedback. AGN are observed to vary over years, and decades, and probably also vary over millions of years. So there's certainly not an equilibrium at every time. But if you average over some suitable length and time scale, which could be the size of a galaxy and a dynamical time of a galaxy, then there should be some kind of equilibrium. Now there's a few immediate implications for that. If you have an equilibrium, then you expect simple scaling relations. So if you plot one galaxy observable versus another, you don't expect a scatter plot, because if they all go to this equilibrium, there should be some coherence in how they distribute over those plots. So scaling relations should exist. Another immediate implication is that gas accretion should drive galaxy evolution. And that's because what comes into the halos, the dark matter halos, so what's in the end going into the galaxy, that's set by the large-scale gravitational field, which is dominated by the dark matter. Right? So that's just channels things through these filaments into the halos. If that's set by the cosmology, then the feedback will have to adjust in the end to that. And this is a very simplified picture. It's a bit more complicated because the feedback can, of course, change the accretion rate a little bit. But it doesn't change, turns out, much the accretion rate onto the halo. So it's not such a bad picture. So gas accretion is what drives the galaxy evolution. And the good news here is that this accretion rate onto the halo, as I just said, is not so sensitive to the feedback. The feedback doesn't really stop filaments from putting material into the halo. So we can predict that quite well. The bad news is that that's not the same. That same is not necessarily true for accretion onto the galaxy. That's found to be quite a lot more sensitive to the feedback. Simulations find that the gas accretion rate is mainly smooth. So it's not dominated by mergers. It's dominated by very small mergers of very high mass ratios, or even things that are not in halos at all. And if that's the case, and if galaxy formation is driven by accretion, then you do not expect much scatter in the scaling relations. Right? The accretion rate doesn't change much in time. And that's observed. Right? So that's understandable. These gas accretion rates that are set in the end by the gravity on large scales, they depend systematically on halo mass, on redshift, and on environment. They depend mainly on environment because they're different from satellites and centrals. If you have a satellite galaxy, it's not at the center of the potential well, so the accretion rate is basically shut off. If gas accretion is dominating galaxy evolution, then galaxy properties should also depend on mass, redshift, and environment. And of course, they do. More recently, it's been emphasized that the nature of the gas accretion changes at a halo mass of about 10 to the 12 solar masses, because at that point, the gas remains hot. Before that, the density is too high, the virial temperature is too low for the gas after it shocks to remain hot. Basically, it would immediately cool. The shocks are not stable, so you just get a cold flow, filamentary cold flow going in. Above this mass of about 10 to the 12 solar mass, where the virial temperature goes above the cooling peak, there are hydrostatic halos in the simulations, hot hydrostatic halos. So we expect that the nature of the accretion is different. In one case, you have this highway of cold material going in. In the other case, you first have to cool it. If galaxy accretion dominates galaxy formation, then we expect bimodality. Right? Galaxies should somehow know about this difference in accretion rate, and that's also observed. Bimodality in bulgy red galaxies and blue disk galaxies is changing. The midpoint is this 10 to the 12 solar mass halo.
What critical mass is for a redshift 0?
It's weakly dependent on redshift, but it's of order 10 to the 12 at all the redshifts of interest. So that's all understandable. If we take this self-regulated picture, we can understand a lot of things qualitatively. Let's look at some other things. So suppose that we take this for granted, what I said, that the outflow rate is determined by the inflow rate, and that there's this equilibrium between the two. Well, if the outflow rate is determined by the inflow rate, so that's set by the gravity, large-scale structure, distribution of structure channels some baryons into the halo, and then the outflow rate adjusts until it's in equilibrium with that. If that's the case, then it's not determined by the efficiency of the star formation, the feedback from star formation. So how much outflow you generate per unit star formation that you form. You should get the same outflow rate regardless of that efficiency. You should get the outflow rate that balances the inflow rate.
Function of some threshold.
If there's some feedback at all, yeah. Otherwise you can't get this equilibrium. So that means that the star formation rate, and therefore the stellar mass, must be proportional to this efficiency, inversely proportional to this efficiency, right? If you generate twice as much outflow rate per unit stellar mass, then you only need to form half as much stellar mass to get the outflow rate that balances the inflow rate. Right? So that's very intuitive as well. When you increase the feedback efficiency, you get less star formation. Fine. And that's also what's observed. Now, what about the AGM feedback efficiency? So how much outflow rate do you generate per unit black hole mass that you accrete? Well, it should also not depend on that, because the outflow rate is determined by the inflow rate. So that means that the black hole accretion rate, and therefore the black hole mass, should be inversely proportional to the efficiency of this process of black hole accretion feedback. And if we generate twice as much outflow per unit black hole mass that we accrete, then we only need to get a black hole that is half as massive to generate the outflow rate that balances the inflow rate. And if the AGN feedback generates the same outflow rate independent of the feedback efficiency, then the factor by which it suppresses star formation should also be independent of the AGN feedback efficiency. So now this very simple idea leads to a bit counterintuitive conclusion. To predict what the effect is of AGN feedback, you do not need to know the efficiency of the AGN feedback. It just follows logically from this ansatz. Now let's do some toy experiments that using numerical simulations we can just turn up and down this feedback efficiency. Right? In some subgroup model we generate outflow rate that depends on the accretion rate of the black hole with some efficiency factor. Here's the cosmic star formation history, star formation rate per unit volume as a function of redshift. The dotted line is what we got in the simulation if we had no AGN feedback at all. And the colored line is if we include some AGN feedback with an efficiency that varies from a value of 0.15 down to a value that's many orders of magnitude lower and a value that's much higher. And this is the value that is actually giving you black hole masses that are similar to the observations. So what changes here is the black hole mass. It's inversely proportional to this efficiency. You change this over 6 orders of magnitude, you get exactly the same cosmic star formation history. So if you may have thoughts, how can people doing galaxy formation predict anything related to AGN feedback? They can't resolve an accretion disk, they can't resolve whatever. Well, of course, some things they cannot predict. But the global effect on the galaxy actually is independent of this efficiency. Because of self-regulation. That's the reason. What about the star formation law? It's the gas consumption timescale. That's what I mean. How long does it take a given amount of gas to convert itself to stars? That's something that these simulations cannot predict either. You have to assume it or take it from observations. Well, if the outflow rate is determined by the inflow rate, it's not determined by the star formation law. Since the outflow rate is determined by the star formation rate, that means that the star formation rate should not depend on the star formation law. Another counterintuitive result. The star formation law should then determine how much gas is involved in star formation. If you convert the gas twice as fast into stars, and you need the same star formation rate, then you only need half as much gas. So that means that the prediction of the self-regulation picture is that the gas fraction, meaning the amount of gas that's involved in star formation per galaxy, divided by the galaxy mass, that should depend on the star formation law, but not the star formation rate. And that's also what you get from these toy experiments with numerical simulations. You implement some Kennecourt-Schmidt laws, basically a gas consumption timescale. You change it, except at very high redshift where you didn't have any feedback yet. Lower redshift, you always get the same result. Right? So to predict how many stars are formed, you do not need to understand star formation. You need to understand feedback. So what are then the consequences besides these?
I would just interject though.
Yeah.
If you talk to star formation people, they would not have said that to begin with. So it does, you do rely on this ansatz, right? The star formation rate is controlled by the rate at which you dump gas into the galaxy. But if you ask the star formation people, do you need feedback? Even now, a lot of them will still tell you, no, you don't need any feedback whatsoever. The star formation rate is set by microscopic physics.
And I wouldn't disagree with that on a small time and length scale.
Right.
But talking over hundreds of millions of years and an entire galaxy, you know, how often the microphysics allows you to form a star somewhere is set by the boundary conditions of this inflow in the whole galaxy. And that's why, of course, when I say we don't need to understand star formation to predict how many stars form, that's indeed only true on these large scales, length and time.
And with the implicit assumption that you can drive gas out of the galaxy.
Yeah,
right?
indeed.
That's the thing that star formation people don't really pay attention to, because they don't think the stars, it wasn't obvious to people that stars drive
Yeah,
out the gas.
it's still not obvious how they do it, but the observations tell us that they do.
Right.
Yeah.
So I'm just trying to give people the impression, you know, this stuff isn't that well. I mean, what you say is correct logically.
Mm-hmm. It's correct logically, which is explanation of why we can do something when we don't understand the microphysics. Of course, we can't say we really understand galaxy formation if we don't understand how a star forms, right? Galaxies consist of stars, so we want to understand that too. But it's not the case what people often think who work on the microphysics compared to galaxies, that because we don't understand that, we can't do anything on bigger scales either.
Right, exactly. But I think this point that the feedback implements this rule is worth really getting across.
Yeah.
It allows you to sidestep the microphysics.
That's right.
Would you, carry on from that, we only allow one channel, say, how I accommodate the inflow rate is only one way by an outflow rate. Suppose I invented another channel, say, producing many more stars in the galaxy. And that logic starts to break apart a little.
Yeah, and the logic is idealized because it's actually not quite true even in these simulations. For example, some of the stuff you blow out comes back later.
Yeah.
You know, stars recycle some of their stellar mass loss providing fuel, not just stuff from the inside, outside. But these things, according to these simulations, are all second-order perturbations on the main picture. But it's actually those second-order things where people are spending most of their time. So if the stellar mass, this is what we concluded logically, right? This is just follows from a feedback loop. If there's a feedback loop, then in the end we conclude all these things. For example, stellar mass is inversely proportional to the efficiency of the star formation feedback. And that means that we cannot predict the stellar mass-Halo mass relation unless we can predict this efficiency. And this efficiency we can only predict if we know how much momentum from supernovae cancels out, how much energy from radiation pressure or supernovae is lost radiatively, if we know all these microscopic processes, which we don't, certainly not in these kind of simulations. So then we have to conclude, which I'll do here in the end, that we cannot predict stellar mass. And if AGN feedback is limiting galaxy formation, then we have to conclude the same thing about the black hole mass, which is even easier to understand. And if you don't know if black holes drive winds through radiation pressure or jets or whatever, and if you can't simulate that, how could you possibly predict the efficiency of this process? So if we can't predict those efficiencies, which I'm saying we cannot, and I would challenge anyone to prove to me that they can, that means we cannot predict stellar mass and we cannot predict black hole mass. And most people would agree with that, but many people would still write papers saying we predict stellar mass, black hole mass. So that's two bits in the heads of people that are often not communicating. So if we cannot predict stellar mass or black hole mass, why do we do this game? And what's the interest then of these simulations? So that's a good question. I wrote a philosophical section on that in a paper. In section 2 of a paper that I will present. So if you want to read anything, maybe just those 2 pages would be interesting to read. And that paper is this one. This led us to start a new cosmological simulation project. The thinking that I just presented, called EAGLE, stands for Evolution and Assembly of Galaxies and Their Environments. We've worked on this for probably about 5 years with a large team. I particularly want to mention Rob Crane, who worked on this project as a postdoc in Leiden for 3 years. Richard Bauer, faculty in Durham. Michel Furlong and Mathieu Schalle, 2 PhD students at Durham that did this for their theses. And Tom Tuins, also faculty at Durham. Claudio Dalla Vecchia, who first in Leiden and then in Tenerife did a lot of work on the hydrodynamic solvers. And also Carlos Frank and Ian McCarthy at Durham and Liverpool, and many other people. It's a project of the Virgo Consortium. So what is EAGLE? It's a cosmological simulation, actually a whole collection of them. We take the Planck cosmology. The volumes vary from 25 to 100 co-moving megaparsec. The largest simulation, the 100 megaparsec one, takes 1,504 cubed particles for baryons and dark matter. So it gives you about 7 billion particles. And a particle mass of a little bit less than 10 to the 6 solar masses, or 10 to the 5 in the 25 megaparsec. So that's about a factor of 10 smaller than the gene's mass in this warm ISM. And the resolution is about half a kpc, better at higher redshift. The hydrodynamics had all been updated to include all the latest fancy modifications to SPH that people have proposed. We include feedback from stars and active galactic nuclei, but only one type of feedback from each. So no radiation pressure versus supernovae, for example. We just say we can't tell the difference at this resolution. The subgroup recipes only depend on local hydro quantities. So not like many people have done, for example, a wind velocity depends on the velocity dispersion of the dark matter or the halo mass. It just depends on local gas density and metallicity, it turns out. The winds develop naturally. We don't say we want a wind, we kick particles with a certain velocity or mass loading. We just dump energy and see what comes out of the galaxy in the end. Now, I told you that we can't predict stellar mass or black hole mass, so we have to calibrate those. And we chose to calibrate them to the observed galaxy stellar mass function at redshift 0 and the observed black hole mass stellar mass relation at redshift 0. And calibrating is what you should imagine there that we do is we take 12 to 25 megaparsec volumes with different parameters and run them and pick the best one. And we don't run thousands, we run tens, because it's quite an expensive business. It turns out if you do that, I'll show that, it's not enough. You can get some models that get this galaxy mass function right, but get very strange sizes. You also need to change your feedback models such that the galaxy size are roughly okay. Once you do those 2 things, the rest follows. Then it turns out you basically fit everything you can think of. That's very interesting. There's different models in EAGLE and different spin-off projects. For example, we're doing zooms of local group type objects and other spin-offs. So what do we do in terms of subgrid physics? Some of it is taken from our previous OWLS project. For example, the radiative cooling rates tabulated as a function of density, temperature, and redshift. Redshift matters because of the UV radiation field, depends on redshift. It's element by element. So we compute the cooling rate for each element individually. And the abundance of each element is followed using a chemodynamics network with 11 elements. Star formation depends on metallicity to mimic the transition from atomic to molecular gas. That also depends on metallicity because the dust content is assumed to scale with metallicity. Black hole accretion and mergers are included using heuristic recipes and stellar and AGN feedback. And I'll say a little bit more about that because that's the main thing. The feedback is what's important. So before I say what we do, just a little bit of discussion. I told you that you need efficient feedback. You need to blow out a lot of gas to be able to reproduce observables. And that's been a problem for a long time. And it's been a problem mostly, and I'll get back to that, because of the way it's implemented numerically. But it wasn't always clear. Often people thought, well, it's not because we do it in a strange numerical way or because we don't have enough resolution. It's because we're missing some kind of physics. Right, so you have to be careful. You can only conclude you need more physics once you know and understand the numerical losses and minimize them. At the current resolution, these different type of feedback really cannot be distinguished. I think when you have Now, of order like KPC resolution, you really doesn't matter whether you talk about supernovae or radiation pressure or even radio mode versus quasar mode feedback. So we do not try to do that. We do need a trick to minimize these numerical losses. And the tricks that people proposed so far is turning off the hydrodynamics such that you kick some gas and you just let it fly out of the galaxy. And you turn off the hydrodynamics outside the galaxy. If you do that, then you don't have any radiative losses, essentially. You know what you're going to get out in terms of wind compared to it's basically what you put in. So you can do something. So that's a trick that's used by most people who use Gadget. You can also turn off radiative cooling temporarily. You don't know for how long, but that's used by most people who use gasoline, which comes has a local history here from McMaster. And then if you say, for example, you turn off the hydrodynamics and you oppose a wind of a certain velocity and mass loading, then you have to say what that wind velocity and mass loading is. And if you let that depend on halo mass, say, or dark matter velocity dispersion, then you're in business because you know what the accretion rate is as a function of halo mass from dark matter simulations. So you can basically predict what you need to get a reasonable galaxy and put that in. And that's what's done by most people who use Gadget. So we don't do this. We have things that depend on local quantities only. So that makes it a little bit more difficult to get things right. But we do need a trick still. And the trick to minimize radiative losses, I'll discuss in a minute. But to get you to understand this, let's first see why you would get radiative losses that are too large in a simulation. Well, suppose you just do the simplest thing possible. You form some star particle and you just inject thermally the energy that you get out of supernovae, say, from that stellar population that's represented by this star particle. That's what Neil Katz, who started this whole business of galaxy formation simulations, did. Well, then you have some problems. And one problem that people discussed a lot is that in reality, much of the interstellar medium is in a cold interstellar phase that's not present in these simulations. So if you don't have that, you have all that mass instead in a warm phase, then the intercloud, well, you essentially don't have clouds, so the intercloud density is too high. Right? And therefore your cooling rate is too high, and that makes your feedback too efficient. Also, if you don't have these strong, clumpy structures in the stellar medium that you get when you have a cold phase, then your star formation is not sufficiently clustered. And therefore your feedback is also not so efficient, because putting a lot of energy in one place is basically a better way to prevent cooling than spreading it out. There's a less recognized problem, although some people have recognized this also for a long time. And that's if you look at what a supernova does, it puts all its energy in a few solar masses, and that's enough to heat it to very high temperatures. Right? The initial velocities are like 10,000 kilometers per second. And then you get very high temperatures and therefore large cooling times and efficient feedback. And what's happening in these simulations is, well, all that energy, if you dump it all the time, is put into all the neighboring gas particles of a star particle, and the heating temperature you get then are orders of magnitude lower than what you get in a supernova remnant. And you get temperatures that are near the peak of the cooling curve, so you get short cooling times and inefficient feedback. Yeah, and one thing that is, I think I have to speed up a bit, so I'll skip this equation, go to the next thing. I just want to say that this is actually not to first order, this independent of resolution. If in a SPH simulation at least, right? Because if you have a star particle and you give all its energy to the neighboring gas particles from all the supernovae that will ever form in that star population, then the temperature you get for the receiving gas particles depends on the ratio of the mass of those gas particles to the stellar particle. And that's independent of resolution. Right? So to first order, this problem doesn't go away if you go to infinite resolution. To second order, it goes away because the distance between the particles gets smaller. So, and why that's important, I will show next. So if you think about when will the feedback be efficient initially, when will you not immediately radiate everything away, when it happens is if you follow this inequality. The cooling time has to be a lot longer than the sound crossing time across a resolution element. This is the resolution scale, h, and this is the sound speed. Because if that's the case, then before a cooling time is reached, before you could radiate away the energy, the particle has already expanded. And that means that thermal energy has been converted to kinetic energy. So that's the relevant criterion. And there's a resolution in there, h. And that's why resolution matters to second order. So if you put in, oh yeah, and then the other important thing is that once this starts cool it expanding adiabatically, that's what it will do initially, then this ratio doesn't change as long as the cooling rate is dominated by Bremsstrahlung. So if the temperature is of order 10 to the 7 or larger, you can, just because the cooling rate then goes as temperature to the 1/2, and it turns out that if you plug in the numbers, then the scaling remains constant. So if it's true initially, it stays true until you get to temperatures that are low enough that you get line cooling. So you plug in numbers, and we've done this in this paper by Claudio Della Vecchia, then you see that this ratio, to get that to be large here, you need, for example, you can do it for an AMR simulation in terms of resolution. You need a spatial resolution of about 100 parsec if the heating temperature is 10 to the 7.5 Kelvin. Or in terms of mass resolution, about 10 to the 5 solar masses. You can see there's only a weak dependence on the particle mass. And it depends on the density as well. So what you can do then as a trick is you can say, well, instead of just dumping the energy all the time of a star particle, in which case this will be very low, and I have a problem, I will say I will always heat a particle to that high temperature if I'm going to heat it. And to use up the right amount of energy, then I'm not going to dump the energy at every time step. I'm just going to do it every now and then, stochastically, say, with an expectation value that gives you the right amount of energy. And that's the trick we've used. And I'll just go for that. So that's the trick we've used. The delta T we can compute analytically, so how much of a heating event we need, how high the temperature should be, given the resolution of the simulation. And we know how much energy we have, so that just sets the probability of heating a particle. Now that means that the energy we put in is certainly initially not radiated away. Later on, somewhere else in the galaxy it might be radiated away, but not initially. But in reality, maybe some of that energy should be radiated away, or some of the momentum should be cancelled if you think in terms of momentum. And that then means we have to calibrate. So the amount of energy, the expectation value for the probability of heating something, that should then be something that we calibrate. And that's what we did. And it turns out when you calibrate that, you don't have to change the amount of energy you inject by orders of magnitude. It's factors of 2 relative to the expectation value of how much energy you have available, for example, from supernovae. And that's because these simulations are not completely crazy. As I'll show, they actually resolve quite a bit of the structure of the interstellar medium. So they get things not that bad.
However, that fraction is just global across the whole simulation.
In these simulations, we make it dependent on metallicity, because you expect higher radiative losses if the metallicity is higher, with a kind of an S-shaped function where at 10% solar you go to a different asymptote. But that wasn't enough. If you do that, then we still have a problem of overcooling at high density. You can see that here. We understand that analytically, the densities actually get higher than this value in the simulation. So what we had to do is we had to increase the amount of energy a little bit with density. Not so much at this density, but at densities of 100 to 1,000. Which don't make much sense because they're still at 10 to the 4 Kelvin in the simulation. They should really be cold anyway.
And the time between these events is still short compared to the accretion time onto the galaxy?
Yes. We do, yeah, there's a good point here. You can't make this arbitrarily high. If you make this too high, then the expectation value of the number of gas elements you heat per star particle will drop below 1. And then you don't sample your feedback properly. And this is kind of maximum you can get away with. That's why I chose this value. Okay, so if we do that, skip this. So that's what we do. We do this stochastic thermal feedback. That means we do not have to turn off cooling. We do not have to turn off hydrodynamics. We don't have to, or we don't, we could have, but we don't include a dependence of this feedback on anything that's non-local or non-gas quantity. So we don't impose any particular galaxy wind velocity or stellar mass holding. We just see what comes out. And this energy that we need per unit stellar mass is a function of metallicity and density. And on average, it's very nearly identical to the amount of energy you expect from supernovae for a Chabrier IMF. And we do that, we calibrate that function here to get agreement with the galaxy mass function at redshift 0 and to get reasonable galaxy sizes. And it's this density dependence that's needed to get galaxy sizes right. Without that, we can still get the galaxy mass function right, but the galaxies are far too small because of numerical overcooling. So time for a picture. Here's a bit of a 50 megaparsec volume. This is a small part of, or small, it's a quarter in each, half in each dimension of the big box. And just to show the dynamic range that you have in these kind of simulations, zoom in a little bit and you can still see a nice disk galaxy. This is a picture made by Richard Bauer, but the color coding is temperature here. And it turns out if you do this, you also get very beautiful galaxies. So here's the stellar light from galaxies, where we reprocessed the galaxies with a radiative transfer code to account for dust absorption. As you can see in the edge-on images here, you can see these dust lanes. So we naturally get ellipticals, disks, the whole Hubble sequence. It just pops out of the simulation once you do these things. Here's the galaxy mass function. Number of objects per unit volume as a function of stellar mass. The data points are observations from Gamma and Sloan. And the blue line here is our 100 megaparsec simulation. And the 25 megaparsec higher resolution simulation is this greenish line. And these fluctuations here are due to the small box size. It just isn't a fair sample. So what you can see is, well, it's certainly not consistent in a chi-square sense with the observations. But qualitatively, we've got the shape all right. So there is the exponential turnover. Over here, we have a resolution effect. That's why it's dotted. And why a higher resolution simulation does a little bit better. And in fact, the discrepancy here is consistent with the systematic uncertainties in the observations. This is only showing statistical errors. And this kind of agreement, which we calibrated together, right? This is not a prediction. We calibrated this. But the fact that we could do it wasn't clear a priori. We could have missed something essential that made it impossible to get this agreement. The kind of agreement we get, if you compare this blue line to the other color curves are semi-analytic models. It's similarly good as semi-analytic models get. It's much better than hydrodynamic simulations have got so far. And that's shown here. The blue line is again Eagle, and the other color curves are other large hydrodynamical simulation projects that have been done recently. This pink line is from Oppenheimer and Gfe. We use this hydrodynamically decoupled winds that depend on dark matter velocity dispersion. Buchwijn and Springel did exactly the same, and they got the green line. They also included AGN feedback. Massive Black did also the same and got this line. And then Arapo, which got a lot of press coverage recently, so that's with Illustris, but it did the same thing also with hydrodynamically decoupled winds that depend on dark matter velocity dispersion. They get this light blue line. So this kind of agreement hasn't been seen before for the simulation. So it means we worked hard to calibrate. And we did it with a more natural feedback recipe, I would say. They might disagree, however.
Can you say a little bit more about precisely what parameters you're fitting in order to do this calibration?
Yeah, so what we do is, so we use this stochastic thermal feedback. The amount of energy that we inject per unit stellar mass formed depends on metallicity and gas density. And the metallicity dependence is physically motivated. It just goes from one asymptote to another, and a crossover at 10% solar. So we just kept that fixed at that value. Then the density dependence also has an asymptote. It goes from 3 times what you get from supernova to 1/3 what you get from supernovae. And the crossover, well, it happens at a density that's not that meaningful because it's actually a kind of an average density of different ISM densities because we don't have a multi-phase medium. It turns out that the average value over the whole simulation is about 1 in terms of how much energy you get from supernovae, but it goes from 3 to 0.3. The 0.3 value doesn't really matter because that's in this regime and there AGN feedback determines everything. The 3 allows us to push this down from something that looked more like that. So it means that we can...
So you're making a prediction about a very dense environment, basically,
No, it's not a prediction that that energy really should be there because it's just something we do to compensate numerical losses. So that's what I was showing earlier before analytically. So if we had higher resolution, we probably wouldn't need 3. You know? We actually don't have enough resolution to predict the efficiency, so we have to calibrate it. But it's not wrong by an order of magnitude.
But you did try some range of resolutions, and so did you have to refix the parameters?
Yes, that's a good question. So we did. So this higher resolution, it's not on this plot, the previous one, we recalibrated the higher resolution simulation here to get this right. So we had to change things again by a factor 2 or so. If you didn't do that, it would be a bit higher.
So there's still an issue of, given a coarse graining, you have to do, and not just you, everybody has to do some tweaking in order to make a coarse grain prescription.
Well, it depends a little bit on how you, yeah, you have to do tweaking, certainly. That's,
well, I know.
yeah.
One might hope, and maybe this is foolish, but one might hope that one would have a robust feedback that's, you know, definitely coarse grain. So you said that one of the key quantities here is the density dependence. Now, whose density is that?
The density of the particle that forms a star.
Okay, so there is no compensation for it being a complicated medium that is represented by that single particle. It is basically whatever SPH tells me the density is, that goes into my description.
Yes, and the density of the gas that receives that energy is very similar because the time step in resolution is such that, you know, when a star particle produces supernovae, it hasn't really got to an environment with different density. And this is to compensate numerical overcooling. It's not necessarily physical prescription. Right?
See,
and so because we have this, because we cannot predict this efficiency of feedback, I think it's absolutely fine to recalibrate when you change your resolution.
okay, but
Because there's no predictive power anyway.
Let's just take your high res compared to your lower res.
Yeah.
If I were to take the high res and say that I am going to make my prescription slightly non-local,
Yeah.
so that the mean density goes down, would I get the same prescription as in the lower res? Or, I mean, I'm just trying to see what happens when you bang on this prescription.
You need slightly different numbers if you want to recalibrate. Yeah.
Okay.
So in this paper, I introduced these two terms of strong convergence versus weak convergence. Strong convergence is when you don't change your model and you change your resolution. Weak convergence is when you recalibrate. And I argue strongly in this paper that weak convergence is the way to go if you don't predict the efficiencies of feedback. And that strong convergence is an illusion in any case. But I don't have time. It's an interesting point to discuss further. Let me just show you, because I'm almost out of time, I think. So I'll just go show a few things.
The previous one was good too. Yeah.
Okay, here's the efficiency of galaxy formation, stellar mass over halo mass, divided by the universal baryon fraction as a function of stellar mass. Blue is the simulation, the Eagle simulation. Here we don't have enough galaxies to bin, so we show them individually. You can see galaxy formation efficiency peaks at about 10 to the 12 solar masses. This is mostly AGN feedback and inefficient cooling. Here's mostly star formation feedback. There's nothing new to that except that now we get a better match to what you would infer from abundance matching, is shown in gray, and therefore you get a better galaxy mass function. Galaxy sizes, this is here the agreement is again unprecedented, but this wasn't a prediction. I show other models that get this completely wrong. It's galaxy size versus galaxy mass. Data points, as well as these, this gray solid line, are observations, and the curves are the intermediate and high resolution models, the 100 megaparsec and the 25 megaparsec model. So if you get these two things right, then you get a lot of other things right. Black hole masses, well, that's recalibrated too, but you get a lot of other things right. Here's the Tully-Fisher relation. Rotation velocity versus stellar mass comes out near perfect. Specific star formation rates as a function of stellar mass. There's somewhat of a resolution effect. Here's the data points again. It's the observations. But this is very good agreement compared to what people had before. Passive fraction. So I showed you morphologically we have ellipticals and disks without putting anything in to get them explicitly. Also, if you check what fraction of the galaxies are star forming, the gray points are the data, the curves are the simulations. It's a little bit too high mass, but that's actually something you could change by changing your subgroup model. You get this naturally without having tried to get it right. Mass metallicity relations for gas and for stars of galaxies. Data points are observations again. At the intermediate resolution, you're a little bit high. It's mostly a resolution effect that allows you to get a very good agreement even at low masses. These are all galaxy properties. What about if we get more in terms of galaxies to the observable space? Color magnitude diagram. Color is here, red is on the top, blue on the bottom, and magnitude, bright on the right, faint on the left. The contours are observations from gamma, and the points are simulation galaxies. So here's the red sequence and the blue cloud. we do get the bimodality. Quantitatively isn't quite correct, but qualitatively it's certainly there. Something completely different, metals in the intergalactic medium. Column density distribution. How many do we see per unit redshift as a function of the strength for carbon-4 and oxygen-6, where oxygen-6 is a tracer of collision ionized gas. Comes out very well too. A lot of things come out well suddenly. Evolution as well. Here's the stellar mass history. I won't show that. The galaxy mass function at all kinds of redshifts also comes out quite well. I'll just show this to finish, because this is interesting, I think. This is showing from a paper that will be posted soon led by Rob Crane, the galaxy mass function in 50 megaparsec volumes, the same resolution as this 100 megaparsec I was showing before. 4 different models, all calibrated to this galaxy mass function, right? To the level at which we don't try to get exactly right, it's too difficult, but roughly right. Now this one, the feedback is constant. It doesn't depend on anything. We just dump the energy from supernovae using this stochastic heating recipe, however. Right? So this is, you could say, is a prediction if you believe that you could predict it, because we didn't try to calibrate it. And it actually does come out well. Here it depends on the velocity dispersion of dark matter, here on the metallicity only, and here on metallicity and density. Now if you look at the galaxy sizes, well, you see it morphologically first. Here's just some images of these 4 simulations. If you look well, you're used to looking at these things, then you see that these 3 all have very strong bulges and are too small. And this one looks more realistic. If you look quantitatively at galaxy sizes, you can really see this. Galaxy size versus stellar mass. This is the model that does relatively well, which has a density dependence on the feedback, and these others just have drastic overcooling at high density. They still get the galaxy mass function right, so you need to look at more than galaxy mass function. But if you only also get this right, then the rest seems to roll out by itself. I'll show a video at the end. Before that, let me just go over my conclusions then. So I told you in the beginning that galaxy formation is self-regulated. That's what comes out of the simulations, and it's also what you would expect. Outflows balance inflow. If that's the case, then cosmological accretion, determined by the gravity dominated by the dark matter, drives galaxy evolution. The feedback is a critical part to get things right. You need these outflows. Cosmological simulations cannot predict the efficiencies of the feedback processes, and therefore they cannot predict stellar masses or black hole masses. They can't. You can't use them for that. There are many ways to get the galaxy mass function right at redshift zeros, but you need to get sizes also right to get the rest to roll out. You don't need anything complicated. A very simple natural feedback suffices. You just need one kind of AGN feedback, one kind of stellar feedback, and that seems to be enough to get both the galaxies and the intergalactic medium right. So in terms of agreement with observables, these simulations are now really catching up with semyon models. But they are much more powerful because you can ask about the structure of galaxies, the intergalactic medium. You can ask many more questions than you can of semyon models. So, and that's what, of course, the fun now really starts. Now that you have a model that roughly reproduces the observations, you can ask interesting questions. How does the gas get into the galaxies, and why do some of these galaxies become ellipticals and others disks? And why do some of them become passive and others not? And what sets the scatter in these scaling relations? You might not get the actual answer that the universe gave you, but you get a plausible answer at least. And then you'd like to vary the models and see how robust your answer is. Okay, I'll just show one movie that Rob Crane made. Here's the evolution of a 25 megaparsec volume at the same resolution as the 100 megaparsec, starting at very high redshifts. Redshift is going down there. The color coding is the density here. Or sorry, it's, I think in this one it's actually the temperature. The intensity is the density. So here you can see the hot gas popping out from feedback in different places. And you can see that the feedback really is violent. And the most violent explosions are driven by supernovae feedback. But many little galaxies everywhere are driving these outflows in the intergalactic medium. And you see the shells being swept up by them, if you look carefully. Some of the hot gas is also hot because of viral shocking. But generally that's less visually striking than the feedback. And remember, if we zoom in on the same simulation, then we see all these galaxy images that I showed you before. You know? We have enough detail to really see the spiral arms, etc.
You're saying some of those bubbles are 3 or 4 megaparsecs across, all driven by supernovae?
No, the biggest ones, those are driven by AGN. by AGN, not at the current time, but they start being driven at redshifts 2 to 3 when the black holes were growing rapidly. And, and that just keeps going later on. Some of it also in the biggest objects is just viral shocking. In the very big superclusters, it's not the AGN outflows, it's just the hot gas shocking as it comes out in. Okay, thank you.
Okay, so we have time for questions. Nick?
Yeah, so one other thing in terms of description. So you're doing a calibration associated with redshift 0, but you have stochasticity in. And what exactly is the control parameter for stochasticity? And when you vary it, does it change how you get other things fitting?
Yeah. Just quickly go back to the. I skipped one slide I shouldn't have skipped. Actually, I don't have the equation. So what we do is the feedback from stars is implemented thermally, where every star particle heats every of its neighboring particles with some probability. If it heats to a temperature of delta T of 10 to the 7.5 Kelvin. And for Chabrier IMF and supernova energy only, that leads to an expectation value of heating 1 gas particle per star particle per lifetime. Now, that expectation value of 1 particle, that depends, that's if you would use all the supernova energy, but we multiply that energy budget by a free parameter, a free function. That's a function of metallicity and density. The metallicity dependence goes from 3 times the amount of energy you have from supernova at very low metallicity to 0.3 times what you have from supernova energy at metallicity that's very high. And there's a crossover at 10% solar. And that's motivated by radiative losses should be more important at high metallicity. And the same asymptotes are also implemented for density dependence. So at high density we get, but in the other direction, at high density gives you, we inject more energy. And that's motivated by the fact that we get densities in the simulations that are higher than what we analytically know we need, where we analytically know that the gas will immediately radiate away its energy before expanding, so it won't do anything. And that is what we need to get the galaxy sizes right. If we don't have that, then because of a numerical problem, we still get these big bulges.
So putting it slightly differently, you could, I'm not sure we're there yet, but you could constrain, and I guess it's actually through the galaxy radii, if some regions didn't do good feedback, then you might say that's really bad for making this fit, which is a derived fit rather than an algorithm fit. So there's an interesting question in how ubiquitous the feedback is in the homogeneity of the medium, which presumably can be constrained by the data.
Yeah, we can say there's outflows necessary everywhere, but that's about it. Anything beyond that, and to see what the actual efficiencies are and whether it is supernova that can do it, don't use these kind of simulations. You want to simulate at much higher resolution the actual processes, which we're doing as well, and other people too. But these simulations are not good for that.
And then another similar issue is whether or not there is an effective redshift dependence of feedback.
Yeah, well, that's interesting.
Built in here, but,
There is, and that's this metallicity dependence. So that was motivated by cooling considerations, but it has a nice side effect, and that's that if you, at fixed stellar mass, go to higher redshift, metallicity is lower, and therefore you have more efficient feedback for the same energy budget. And that's exactly what you need. You need early feedback in these models. Now, if you think what people did before is they implemented things that depend on velocity dispersion, and they're still doing that, so Illustrious does, for example. That has the opposite effect. Fixed stellar mass, the higher redshift, the velocity dispersion is higher. And higher velocity dispersion also at fixed redshift corresponds to higher mass, where you need weaker feedback in the models. to get the shape of the galaxy mass function right. So that if you tune such a model to get the galaxy mass function right, you automatically get the evolution wrong. So in that sense, but I wouldn't say that that's the way the universe solves it. But it could be part of the answer.
Further calibrating observations.
Yeah.
So what's determining the balance between the AGN and the star formation and feedback mechanisms and over time? Are they both important all the time? Does one dominate earlier than later?
Yeah, that's a good question as well. So it's interesting. The black hole feedback actually have almost no control over, because this is what we can change. Is we can change its efficiency, but as you see, it doesn't do anything for the galaxy mass function either. It doesn't do anything either. All it does is change the black hole mass. But the black hole mass is actually not interesting in these simulations because it doesn't do anything, because all the feedback is controlled by this efficiency, and because of self-regulation, it doesn't matter what you use. So whether you get black hole masses right doesn't actually matter. Now, what we can do is we can control through the accretion model on a black hole, so we can control where it starts to accrete efficiently. And that's basically where AGN feedback kicks in. Every model has some free parameter that deals with that. But then once it's efficient, what it does to the mass function, we have no control over. Now, we do need, to get the galaxy mass function right, you actually do need to, sorry for scrolling through these things, giving you a headache. Just want to get a mass function up there. Yeah. So here is AGN feedback. But to get this stuff around the knee right, you need the galaxy feedback from star formation to get weaker already here. Otherwise, you don't get this slope right. Then it gets too steep, more like the mass function. Right? The mass function of dark matter halos is like that. So you need to get the feedback to get weaker and weaker as you get to higher masses to push this down. And because it gets weaker and weaker, you would not get any kind of shutdown. You would just continue, and that's why you need the AGN feedback then.
So I might comment about that. In the higher resolution, smaller block simulation we can use. So instead of tens of megaparsecs, we're talking a couple hundred kiloparsecs or whatever. We've just been starting to put in the AGN. You get the same sort of behavior below the knee. You actually get the knee properly using just the default values for the supernova input, radiation feedback input. You still get a bit of a turn down actually. It's just not as steep as this one.
Remember what I showed there. You have to be careful, because I showed also what happens if you, this is when you don't calibrate anything. You have constant energy here. You do get, so you see, when I say it's too steep, it's,
Well, we're not using constant energy, of course, because we're actually resolving how much energy goes into the ISM. And that does vary with the number density. Right? So we're capturing what you're putting in that number density dependence. Because it is true, right? If you go very high densities, you get a weaker feedback. Because you do slightly increase the radiator losses. Not by a lot, it's only like the end of the 1/7 or something.
That's possible, yeah. I mean, it would be very interesting to see what you find. I was never clear to me exactly how it goes, actually, because you go higher density, you have higher cooling rates, but if you have higher star formation rates as well, in nonlinear star formation law, you also dump more energy. So a priori, it's not actually clear if you...
Well, the star formation rate, we don't put in a rate. We use a prescription which just says if the gas is self-gravitating above a given density threshold, typically 100 or 1,000, then we just turn it into star.
Yeah, but what I was saying, a priori, you don't know whether higher density gives you more or less feedback.
Well, it gives you more or less feedback per stellar mass. It's always the same feedback per stellar mass, but the net
per unit
result,
volume, I mean.
Yeah, then per unit volume. It does actually reduce it because you're putting these supernova going off. The first few that go off are going off in dense gas.
Well, that's good news because that's what we need.
Yeah, exactly. That's what you see.
Yeah.
So it's in the same sense that you're doing it. But you do get a bit of a roll-off at high. It's surprising. I was surprised you get a bit of a roll-off above 10 to the 11 or whatever stellar mass.
Yeah, some of this you get even without AGN feedback,
exactly.
Also because the cooling time, I mean, that's the classical Reason-Osterreicher argument, right? At this mass, the virial temperature is such that the cooling time becomes long, and therefore galaxy formation is inefficient, and this is a typical mass of a galaxy. To first order, that's right. To second order, since the density goes up in the center, you always have some gas cooling out in the cooling flow, and you get too much. But you get some rollover from that.
Yeah. The other thing that you get wrong, of course, is at redshift 0, you get too much star formation. the integrated stellar mass is okay, but this current day star
Yeah.
formation is like 2 orders of magnitude or an order of magnitude too high.
Yeah.
Okay, so we're going to be taking Joop out for dinner. Please let me know so that we can make arrangements. And now we're going to go out for cookies. And let's thank Joop again.